We're going to get started in a minute or two. John is showing us Venus from Halifax, Nova Scotia right now. And our guest today is Frédérique Baron, who is coming from the Institute for Research on Exoplanets. You're the Education and Public Outreach Coordinator for the Institute of Research on Exoplanets at the University of Montreal, correct?
Yeah, exactly. It's a really short title. It was all great.
Super So it is 8:01. We are officially live on YouTube, and we'll get started. Welcome, everybody. For those of you who have not met me yet, I am Jenna. I'm with the Royal Astronomical Society of Canada. We usually have our co-host Ryan here today. Ryan could not be with us tonight, but don't worry, we still have a bunch of awesome people here. We have a new guest who's joining us today, just for today, to show us some images of the sky. That's John, who's operating his scope from Halifax, Nova Scotia right now. John, we have a new project coming down the line soon, which I can't say much about, but it will be happening later in June, and John will be back with us again for that. So keep an eye out for him again. And we also have Frédérique Baron here, who is, who, as I mentioned, if you were here earlier on in the stream, is the Education and Public Outreach Coordinator for the Institute for Research on Exoplanets at the University of Montreal. She studies brown dwarfs. Yeah, I did it. She studies brown dwarfs, and she's going to share a bunch of her research with us and what happens at the Institute for Research on Exoplanets as well. But first, I'm going to go over a couple things that are happening coming up in astronomy, and also for the folks who are joining on the Zoom. Just a heads up, if you want to talk to everybody and not just us three, make sure that you change your little bar from all panelists to all panelists and attendees, and then you'll be able to talk to everybody. And hello again. It's nice to see familiar faces in here. So what we've got tonight, briefly, John's got Venus up, so that's what we're seeing right now is our live view of Venus. Venus has been getting, I think it hit peak brightness, didn't it, John? And
yeah, I think it was a little while ago. And because it's definitely a crescent right now, and I can reduce the brightness a little more, and we'll see that it's even thinner than we're showing here. You know, we can, because there's not much of it there. And
there's not much left.
It's noticeably dimmer too in the sky. I don't know if we can even. So I'm literally on the sidewalk, and Venus is right in between these two houses right here.
Wow.
And we're gonna lose it in just a minute here. And I know Mercury's right below it in conjunction, but Mercury's definitely lost behind those houses.
Yeah, no worries on Mercury. And on that note as well, it's tomorrow evening, Mercury and Venus will be nice and close together. They will be in conjunction. So if you get the chance, right after sunset, head out to and get a nice view to the west, and take a look for those two spots next to each other. Mercury is going to be much dimmer than Venus. Oh, look at that nice crescent there.
There we go.
Wow.
There we go. So if we want to, this is kind of neat. So this is a program called ICAP. It uses a little Celestron planetary imaging camera. And what we can do is take a little video. I'll have to fix the file name later. But I can take a little video and then drop it into a program called Registax. And that'll take all, so here we've got 300 frames, I'll take 1,000 frames, and it'll turn that video into an image. And that image will be much clearer than we see here. And the computer will clean it all up, and it's really neat.
Cool.
So
It's neat to be. Yeah. If you get it all sorted out, we can share it afterwards. Venus is really cool because it's getting closer to us now. So it's moving in between us and the sun. And so because it's getting closer, it's getting bigger, but it's getting less lit up. So for a while, even though the proportion of Venus that was getting lit up was smaller, Venus was getting brighter because it itself was appearing bigger in our sky, which is like the world's most counterintuitive thing. But it's really neat to think about. And now it's starting to get dimmer because even though it's getting bigger, it's really just a tiny, tiny sliver left behind. Now is the time to look at Venus, because if it's going to be disappearing between us and the sun for a little while. And then after that, it will only be visible in the morning. And who wants to get up at 5 a.m. to look at planets?
Not me.
Nobody.
Well, maybe some.
The other interesting things that are happening on Wednesday next week, there will be the first commercial crew launch from American soil, first launch of anybody from American soil into space in the past 9 years since the shuttle program. And it's going to be on the Crew Dragon, which is the spacecraft built by Elon Musk. So it's an exciting new step in space travel. We are planning on hosting a watch party for that on our Facebook group, the RASC Facebook group. So if you want to join for that, that's at 4:32 p.m., assuming that they don't make any changes, on Wednesday next week. And then the other last piece of interesting astronomy news is that there's a new space telescope that is named after a woman, which is the first time we've had a space telescope named after a woman, which is very exciting. And that woman is, it's W First is the telescope, and that woman is, yeah, it's so exciting, is Nancy Grace Roman. And Frédérique, I know that you know more about Nancy Grace Roman than I do. Can you tell us a little bit about her?
Well, she's known to many as the mother of Hubble, because she created the astronomy space program at NASA. As you know, NASA as a mission is looking a lot at the Earth, but she really pushed so that NASA would look at the rest of the universe, not only our planet. And she even has her own Lego figurine, which I have in my office, and I'm at home. But I would have really liked to show you, because there's like a tiny Hubble, and then there's like a picture of a nebulae, like it's the kind of object that she studied the most. And there's like the tiny like Nancy Roman. It's really cute. Anyways, I'm really happy that for the first time there will be a space telescope named
after a little Nancy.
Woman. Yeah, it's pretty great.
That's really exciting.
I will put the
Nancy Roman
picture.
Is a minifig. Is that the case?
Look here. I've put a link to the.
Yeah. Oh,
the
you
Lego,
have a picture.
so you can see the tiny thing. Yeah. If you go on the link that I've just
John, I'm going to steal your screen share for a minute.
I think it's sold. Yeah, it's sold as 3 like important women in the field of astronomy and space. And it's really cute.
Whoops. Cool.
It's my favorite one of the bunch.
I'm going to
with her gray hair.
The screen. There she is. So cool. That's awesome. So a very exciting time in space history.
The tiny Hubble.
We do have the reason that we the reason that we have less stuff going on right now is because it is with the COVID lockdown. Most of the telescopes around the world are shut down. So we don't have as much new information coming from those telescopes, but there's a lot of cool stuff going on. Okay, so our structure for tonight, Frédérique, I'm gonna hand it over to you momentarily. Looks like, oh, good, you're still there. And then we're gonna chat about Frédérique's area of research, which is brown dwarfs, and it's gonna be really exciting. I'm stoked to hear about it. And then afterwards, later into the evening, John's gonna come back and he's going to show us, we're going to do our best to capture a Starlink passover of some of the satellites. It's a dimmer one, and it happens at 10:02 Nova Scotian time, so 9:02 on our time here, so that's about an hour away. We're going to do our very best to catch it, and then once we do our best to catch that, we will take a look at some other stuff that's up there tonight. Because luckily, for the first time at one of our star parties, finally we have clear skies. So it's very exciting. Alrighty. I think I may be cutting it a little bit.
Well,
there we go.
Everyone, before I pack up this
all right, Frédérique,
Yes.
Yeah, so I was just going to say, before I pack up the scope, let me just show folks how I took that picture of Venus. Is that okay, Jenna?
Absolutely.
Can you hear me? Okay.
Yeah, we have a little bit of a lag issue, but go for it.
Okay. So here's the scope I'm using, just a little 4-inch refractor, and it's on motorized mount. And then the camera is just a little tiny thing. It's called a Next Image 5 right here. I just put it right where the eyepiece would normally go. And so that goes right into the computer, and it makes it really easy to take images of planets and stuff. And that's only about $100 camera, so it makes it really easy to do what we just saw. And later tonight, we will show you that picture.
Perfect, awesome. Thank you, John.
I'm excited.
All right, Frédérique. Yeah, I'm super excited. It's gonna be great. Frédérique, I'm gonna hand it over to you. Would you be able to tell us a little bit about your research, please?
Yes, well, I'm very happy to be here today to talk a bit about brown dwarf. As Jenna said, I work at the Institute for Research on Exoplanets, which, I mean, the title kind of says it all. We mostly work on exoplanets, so those planets that are around other stars than our own sun. So brown dwarf, why, how? I will discuss that a little bit. So I'm very excited because I'm mostly, again, as Jenna said, I mostly do outreach. And so I mostly talk about exoplanets, how to find them, and then the search for life and aliens and all of that stuff, which is not exactly the kind of research that I do, because I work on those objects that are very big planets or really small brown dwarf, which are maybe the same. I don't know. I think that's the big questions. The question that really guides my research and the research of other people in my field. It's, what's a planet? That's surprising, right? We kind of feel that we know what's a planet. We live on a planet, like Jupiter is a planet, and then Venus is a planet. That feels like really, really certain. But we have a definition for what's a planet. That seems really clear. And we also have definitions for what's a star. That seems really clear. We also have a definition for a brown dwarf. But then the lines gets a bit blurred when you have some weird object. So I guess this is what I'm going to discuss with you today. And I'm also very excited because I've been participating in the project that's called Astro at Home. We discovered the universe, so it's for kids. We do it in French at 10 a.m. on YouTube, and also at 2 p.m. In English, across Canada, for kids age 8 to 12, and those that are young at heart, like everybody. And I've talked about aliens and stars and the Earth, and my last one was about brown dwarf, because we have time. We've done like 50 sessions up to now. And I was really surprised to have kids really excited about brown dwarf, because this never happens, not just for kids, like for everybody. It's called brown and dwarf. Like a brown small thing is just like, it's a worse name, but still it's really, it's really, I think it's really interesting. I really love those objects. So before we go further, I will share my screen, and then you will have, that's funny, you will have to excuse my French, but literally, because my slides will be sometimes in English and sometimes in French, but I will talk with this worst, terrible English, and I think it will be okay.
Your
but
English
before
is
we go in,
spectacular.
thank you. I do my best, and I try to speak slowly so the H comes at the right place, but I tend to talk a lot about ham, but that's just the way it is. Okay, let me go to what's the star, and then we'll define what's the planet, and then we'll see what's the problem with the relationship between stars and planet and brown dwarf. Lots of things in the chart. Nothing.
Yeah. So just a heads up while we're here, I'm also going to mention, yes, the video is choppy, and I found it a little bit choppy too. We have a little bit of a lag. But unfortunately, as far as I know, the only way to fix that is completely restart. And I don't want to do that to everybody because it's confusing and we'd lose folks. So I do hope that we can, at least I'm still getting the audio. I'm not sure, even if the video is a little choppy, hopefully it'll resolve itself as we continue.
Let's keep going. And if it's too hard to follow, you decide what we do. We shall survive. Okay. I like you, Heather. Okay, so stars. so stars like the sun, we know that there are stars that are much bigger. Those are the big O stars, and then we classify them against spectral type. Yeah, that is an HR diagram, Katrina. So you have here the luminosity against the color, which is the B minus V, yeah, color, yeah. No, B minus J color against the luminosity over the magnitude, and you can translate the color, which is what you observe, into a spectral type. And this is how we classify stars, with the biggest one here are really bright, and then down to the main sequence towards the M red dwarf. So those are the smallest stars. They're also the most common around the sun. So 75% of the stars around us are M dwarf. So if you ask me as a professional astronomer, what's that star? I won't be able to tell you. That's the thing with with professional astronomer. Like if it's not an Orion, I won't be able to tell you. I'm sure that you know as an amateur astronomer, but I don't. So I will tell you that's an M dwarf because 75% of stars, like 3 out of 4, they are M dwarf. And I will tell you also that there's a planet around it because all stars have 1 or more planets. So, but that's all what I can tell you because I don't know my stars. So this is how we classify we classify stars. So there's a sentence to remember the name of the star. Well, the order with the O, the biggest one, and the M dwarf, the smallest one. And it's O, be a fine guy, kiss me. So O, B, A, F, J, K, M. Those are the stars. And if you want to add the brown dwarf, then you add lovely Timothy Young. So you can also do oh, be a fine girl, kiss me, lovely Theresa Young. You can choose as you wish in that sentence, just to remember. So the biggest stars are the O, and the smallest one, the red dwarf, are the M. And then you have the brown dwarf, L, T, and Y. It's actually quite recent that we've given them letters. Well, as you see, even for the stars, like there's no alphabetical order. It's like often in astronomy, it was like decided 200 years ago, and then we kind of kept the same letter, even though it doesn't make sense anymore. It's like a planetary nebula. There's no planet. There's no. Yeah, it's. I guess a nebula. It's in French. It makes more sense because it does mean like just like you cannot exactly. Nebuleux means hazy, so it's round and hazy. So it looks like Uranus, okay, I guess so, in 1850 looking through a telescope.
It's funny how those things carry over from the past, those little like, looks like a planet to me. I'll call it a planetary nebula. It has nothing to do with planets. That's fine.
yeah, and now we know. And still that's the name that we have for those objects, so we keep going with that. And I will keep my lovely Timothy Young assignment because I don't like yours.
I don't want to say anything on the stream. Simon Poole from Calgary is suggesting inappropriate replacements for LTY.
No, I like mine better. I will keep that one, especially as I use it sometimes with kids. So I will keep mine. So when you think about a brown dwarf, you have something like those L, T, and Y that is intermediary in mass between a low mass star and a Jupiter planet. So to be a star, you have to be about 75 Jupiter mass. Don't ask me in like solar mass. I just know Jupiter mass. This is my unit of choice for mass. So about 75, it depends on the metallicity. So it can be slightly more or slightly less. What happened at that mass is that the object becomes massive enough to be able to fuse hydrogen, and then you actually have a star. I have a Q&A thing.
Yes, I can keep an eye on those for you if you want to keep going. Okay. I'll read them out. Have you got it?
Oh yeah, I see it. I will go back to you, Leon.
Okay.
Because I will show you a picture of what a brown dwarf look like soon-ish.
And for those, and for those on the YouTube channel, we'll read out the questions as we go as well.
Oh yeah, because that's a good point. I've forgotten about the.
That's okay. I can always read them out for you. No worries.
Great. Okay, so if you have something that is over about 75 Jupiter masses, then you have a star. It lights up. It makes its own light. That's a star. So that side is pretty clear. And then a planet. To be a planet, you have to be round. So you have to be you have to have enough mass to be round. So there's gravity on your object. You have to orbit a star that is not our sun. Well, if you orbit our sun, you're a planet. If you orbit a star that is not our sun, you're an exoplanet. So there's the slight difference here. Then there's the Pluto case. So you have to have cleared the neighborhood around your orbit, so to be a planet, which for exoplanet, that's not something we can tell. We don't have enough information on all of the exoplanets to be able to say if they have cleared their orbits. But still, that's really a case special to our own solar system. And then the last thing that you need to be a planet, you have to be less massive than 13 Jupiter mass. So if you are less massive than 13 Jupiter mass, you don't do any kind of fusion. But at 13 Jupiter mass exactly, this is when deuterium burning starts. So that's the first element that will burn into the core of an object. So if there is that burning, even though it's something that happens fairly quickly into the lifetime of a brown dwarf, then you're no longer a planet, but you are actually a brown dwarf. And let me see. Okay, I think I have the slide that I want to show you here. Okay. We'll go back
I'm personally
here.
really enjoying that they're both in French and English because it's expanding my French vocabulary.
Yeah, I tend to forget that sometimes I have things in French, some things in English. It just gets all mixed up into my head. So
it shows the amount of knowledge that you have. I mean, like the fact that you can bounce so quickly back and forth between French and English isn't just amazing, and I'm extremely jealous of that.
But it gets really confusing because there are terms. I mean, physics. I've learned physics, even though I went to University of Montréal, so I did my studies in French. The books were in English, but there are terms that you cannot translate directly. It's like faux amis, like there are words that is the same but doesn't mean the same.
Okay.
So you have like a angular momentum, which is what happens when you have like like an ice skater that it goes faster when she has her arm, and then it's slower when she opens her arm.
Mm-hmm.
So this is angular momentum. But if you translate it directly, moment angulaire, it's not the same thing. So that's really confusing. So sometimes, yeah, translation
that's tricky.
Weird. Oh. It's tricky, yeah. The worst for me, it's Greek letter. That doesn't make sense in English.
Oh no.
Okay, anyways, there was let's go back to my favorite subject, the brown dwarf.
Yes, sorry, I didn't mean to distract.
No, it's okay. I'm happy to talk about it. So to be a brown dwarf, though, you have to be between 13 and about 80 Jupiter mass. This is where you have all of the L, T, and Y dwarf. There's something really interesting is that even though you have here 3 spectral types, they will all have about the same size, the size of Jupiter. And all of the so every spectral types, you can divide them into subtypes. So you have M0, M1, M2, M3, and 4 to up to 9. So M1 to M6, they are mostly stars. M6 to about L4, they can be either star or brown dwarf.
Oh man.
And then when you go to L6 and T and Y, then they are mostly brown dwarf, but also maybe planets, because it all depends on the mass. And the information that we have when we observe them, it's photometry. So we have flux. So we know how much flux there is, how bright they are. So we measure the flux, and then if we can have the age of the object, then we can use models to maybe give them a mass. And once we have a mass, we can say what they are. So this is what I'm trying to show here. Let's look on the left-hand side. So here you have the effective temperature. So when you measure the flux, what you get is the effective temperature according to the age. And let's say that you have an object that is about 2000 Kelvin. So you can see yeah, let's say this line. So 2200 kelvins. So you see that according to the age, you can have something that is a star. So this is the blue regime. It could also be a brown dwarf in green, or it might also be a planet. And the only information that you have, if you don't have the age, it's the temperature. So it's really hard to tell. And that seems crazy, right?
Yeah.
It's hard to tell if what you have is a star, a brown dwarf, or a planet.
And I have a question. Can I ask you right now?
Go ahead.
Can a brown dwarf turn into a planet over time as it gets older, or no, it would just change temperature instead?
Exactly, because what happens is that if you form, let's say you form a brand new brown dwarf, and it's 50 Jupiter mass. So as it's brand new, it's going to be bright-ish. Like it's not a star, but it's going to be bright-ish. It's going to fuse deuterium at the beginning of its life. So let's say here you have it. It's brighter. You see it's bright, and it stays bright because it's fusing deuterium. And if it's like over 60 Jupiter mass, then it will also fuse lithium. So those are the two elements that you can fuse into our heart of a brown dwarf to its core. And then when you reach hydrogen, then it's a star. So you can fuse deuterium or maybe lithium. So here you see it. There's like two bumps because you have deuterium and lithium. And then what happens after you finish burning? Well, the brown dwarf will just cool with time. And when they cool, they just become dimmer and dimmer and dimmer. So they won't transform. But if you look at something here that is like really cold, 500 Kelvin, it's really hard to tell if what you have is of planetary nature of it or if it's a brown dwarf.
Oh man. Wow. That makes it very tricky.
That makes it very, very tricky. And so I went over the definition of an exoplanet, but what I want to show you here is that there's this graph where you have the density against the mass. And you have the three regime. So you have stars, where the density decreases with mass. And then you have the giant planets, so Jupiter-like planets, where the density increases with mass. And then you have the low mass planet, where it depends if you have like a rocky thing or water world or whatever, like in the exoplanet world. And it's quite clear that you have, like, there's a difference between a star and a giant planet. I mean, they don't follow the same curves. And there's also a difference between the low mass planet and the giant planet. They also don't follow the same curves here in density. And this pink line, that's the 13 Jupiter mass limit. And here there's nothing. So observationally, yeah, can I say that?
Yeah.
Yeah, okay. I wasn't too sure if there was an extra syllable or something.
No, observationally sounds right.
Anyways, what you can see, that world. So when you actually look at brown dwarf or giant planets, if you have the mass and the radius, then you have the density. So that's something that you can measure. But the mass you cannot. It's really hard to measure directly, and so it's really hard to tell if what you have is a giant planet or a brown dwarf. And what you see here is there's no really difference like in regime. And the limit that we've put at 13 Jupiter mass, it's only because of deuterium, but we cannot detect it, that element. First, because it burns really quickly, and there's like just not enough to be able to detect it.
So if we theoretically could detect deuterium, would it be easier to identify brown dwarfs?
Sure. If we could say there's deuterium there, or if there were and it's past, then that would be super easy to tell. Well, if we could, that'd be easy, right?
That'd be great.
Then we could then we could say yes, what we have is a brown dwarf. But actually now we cannot. What we can is infer the mass according to models. And what we have is that more often than not, we have object. We measure the mass, and it's like 12 Jupiter mass plus or minus 6. What do you do? How do you? What's the name? What's in the name? I don't know how to call that object. So some people will call it a planet. Some will go with brown dwarf. Some will go with planetary mass object, which I guess if you're not sure. Maybe it's a good way to call it. So
it's like not deciding what you want to do. It's staying very neutral.
Yeah, exactly. But there are people that really don't want, because I mean, planet it's like it's cooler. Like, yeah, I found a planet. Like a brown dwarf is like, who cares really? But a planet, I mean, you have more funding with planets than with brown dwarf.
Oh man.
But there are people that really think that you should use planetary mass object just because you don't know, you're not sure. Even if the object is orbiting a star, it might be just a binary system with a planet and a brown dwarf. So the way to be able to tell if what you have is a brown dwarf or a planet, that would be formation. If we can have an idea of how that object formed, then we can know if it's formed in a disk like a planet or like a star. So I have another graph elsewhere. I will show you. I will
Right.
stop my share screen and I will share another screen.
While you're doing that, there was a couple questions that came in.
Yeah.
One was, where do hot Jupiters fit in this? Katrina was trying to figure out how to visualize all of this. How does that work?
That's a good question. So, okay, I think I will answer with another.
Sorry.
No, it's fine. This is what I'm here for. They have this in English somewhere. Let me see. Here, okay. Let me share that. Where are you? You're here. Okay, share. Okay, so
Perfect.
all Jupiter, all brown dwarf, they're about the same size. So if they're the mass of Jupiter or 70 mass of Jupiter, so between 13 and 70, this is a brown dwarf. They're all about the size of Jupiter. A hot Jupiter is a planet like Jupiter, but that's really, really close to its host star. Like so close that it will go around its star in about 4 days.
Oh,
So
wow.
that's really, really close. And for once, that's a really good name. They're about the size and the mass of Jupiter, and they are really close to their host star, so it's really hot. Hot Jupiter, that makes a lot of sense.
They finally got a name right.
Yeah. So it's really a different kind of planet. So a hot Jupiter would be closer to a Jupiter-like planet in terms of composition. Actually, we know that Jupiter, like hot Jupiter, they cannot form where they are. You cannot have gas so close to its star. So when you form a planet, I will go to my okay, so we have a nice link to formation. That's really awesome.
Perfect. Thank you,
Yeah,
Katrina, and thank you, Frédérique, for making that connection.
They have it here. Yeah, okay. Okay, so that should work. So when you form a star, you have a molecular cloud that will collapse, and that will form the star. And around it, you will form the protoplanetary disk. This is where you form the planets. So this is what you can see here. So you have the star forming, and then you have the disk. This is the reason why, and this is conservation of the angular momentum. This is why you have a disk. So that's interesting too. And this is why all the planets in the solar system, they're lying in a disk, because they all form in a disk. And we know from formation that if you look at the solar system, you have 4 small rocky planets, and then you have Jupiter and all of the gas giant. So if you're close to the star, the sun in our case, what you will have is lots of rocks closer in, and then the gas and the ices will be farther away in the disk. Where this is where you will form the gas giant, but also the ice giant, Neptune and Uranus. So Jupiter, we actually think it formed a bit closer in, but not much, and then it went inwards, and then it went to its actual position in our solar system.
Really? Jupiter, our Jupiter.
Yeah, I know that's something that I think it's really interesting. It's really hard to explain, like our solar system. People have been trying to simulate it, like make it in a computer, and it's even just the 4 rocky planets. It's really hard to have Venus and the Earth at about the same size and so close, but Mars really, really smaller than the Earth. And so even just those 4, but if you add the gas giant, it's not doable. I mean, you cannot have like a really small Mercury and then Mars. It's really hard. So one of the explanation, this is the Grand Tech model, you have Jupiter moving in and moving out.
Interesting.
So what we know about Jupiter-like planet is that they have to form in the outer part of the disk, about where our Jupiter is now. So if you have a hot Jupiter, you know it cannot have formed so close to its host star. So it means that it migrated in. And there are a few mechanisms that can explain how a planet can move into a disk. It can be just interaction with the disk itself, but also when you have a really young disk, you also have lots of small planetesimal, and they will just interact with each other. And this is how you could have what is called type 1 migration, where those planets can come so close to their host star.
Oh wow, that's cool, huh? That's super neat.
It's really surprising. like even our own solar system, it's really hard to explain. So when you think about other solar system, well, other stellar system around other stars, there's a lot to explain.
And there's a lot to learn too. This is certainly, I guess that's why all these planets get all the darn funding.
Yes.
Instead of the brown dwarfs.
They're closer to our own heart.
Yeah.
And what I wanted to say earlier about formation is that, let me go back, is that if you have something that is around a star, that something is like, let's say 12 Jupiter mass, according to models, plus or minus 6, and you cannot tell if there's deuterium or not. So the goal would be to know how that object formed, because it could have formed into a disk. We know that there's two main mechanisms that we've theorized to explain the formation of planets. One is core accretion. It explains really well the planets that are closer in, and like formation of rocky planets where you have, it's like pebble accretion. So you have two pebbles, like really small dust that just collide together and they stick, and then you have two more and then it stick, and then you make a bigger ball of rock. So that will explain pretty well the formation of rocky planets, and even the gas giants that are really much closer in, like our Jupiter. Mm-hmm. But if you think about the brown dwarf or the giant planet that really intrigues me, they're really far away in the disk. They can be up to between 20 times the 20 AU, so 20 times the distance between the sun and the earth, up to 2,000 astronomical units. So they're really far away in the disk. So if you have something that is 1,000 astronomical units in a disk, and it's 12 Jupiter mass, how do you call it? Well, if it formed like a planet, you would call it a planet. But it could also form just by collapse of the molecular cloud, like just like a star. And we know that brown dwarfs tend to form like stars, and they could form objects down to 1 Jupiter mass. So we know that the mechanism that form planets can form planets that are up to even maybe a bit more than 13 Jupiter mass, but also the mechanism that form brown dwarf, they can form brown dwarf down to 1 Jupiter mass. Wow. So to me, that means that nature does what nature does. I mean, sometimes you will have a brown dwarf, sometimes you will have a planet. Humans, we just like to put things into boxes, but it doesn't mean that something has to, like a 12 Jupiter mass object has to form like a planet or has to form like a brown dwarf. Maybe it just forms like a bit of everything. And this is what my PhD thesis showed.
That's really cool. And it is very much human nature to be like, I need to categorize this into a thing that I can name, even though it's not at all how you would how nature behaves.
Yeah. And even if I say, okay, it has to form like this way, this is a brown dwarf, has to form this way, this is a planet. Well, nobody can live long enough to like go close to a baby star and just look. Yeah. That's not something that we can do. And if you have something that's really old, you cannot tell how it formed. So this
is why I find it so cool that that this is like that it's so hard to figure this out. This is fascinating. There's a question from Janine. Are you saying that a brown dwarf can form from one molecular cloud? And I think the answer was yes, right? Like it can.
Yes, this is the preferred way to form a brown dwarf. It's like a star, so from the gravitational collapse of a molecular cloud. And if you have like a really high density and some instabilities, then you can build a core that will be much lower than the gene mass. So then you'll be able to form a brown dwarf.
Okay, cool.
No, a cloud.
So in the
it's
question,
actually bigger. Like, yeah, it's not just one cloud, one brown dwarf. It's like in a cloud, you will form lots of little, like there will be lots of little instabilities, and then maybe I can show you a simulation, but you'll have like lots of little instabilities, interaction, and then you will form stars and brown dwarf at the same time. Let me show you if I have something.
So for those watching on YouTube, the question was, does one molecular cloud turn into one brown dwarf? And Frédéric's answer was not necessarily, and it often creates lots of stuff. Also, I'm sure, Frédérique, that you're going to talk about this, but my favorite, maybe I'll save it. I was going to talk about or mention the actual color of brown dwarfs.
Yes, that's something I want to say.
Okay,
yes.
I won't say anything.
No, that's not the one. Do I have it? Oh, yeah, there you go. So this is a formation from a molecular cloud. And okay, so you see you have a molecular cloud. I mean, I know it lags a little, but you have like the little white dots everywhere. So those are like baby stars or baby brown dwarf. So you have more than just one forming at a given time.
Cool.
And this is how you have like high density of stars in a star forming region. And this is also how you can form binary system, because they have to form close by if you want to have two or more stars in a given system, or a star in a brown dwarf. Okay, and then cool. I think I will go to the color, because that's
okay. And then just for timing's sake, we have another about 15 minutes or so, and then we got to jump to trying to catch the Starlink satellites that are going by. Right. And I have a couple questions saved up for you as well.
Okay, so I will just go to this. Share screen again here. Okay, so brown dwarf. I told you at the beginning that this name is quite terrible because it's brown, but they're actually not brown. I have a slide in English. So they're not brown. And here you have, those are artistic rendition, because I will show you next an actual picture of a brown dwarf, and you will see that we cannot tell their color. But what we know is that they're really faint and they're visible. So you cannot see a brown dwarf. I think I had a question, what's the naked eye brown dwarf? That's not a thing, because you don't have infrared eyes. You need to see them in the infrared. And they're really, really faint. I mean, I will show you too that there are brown dwarfs that are really, really close to the sun, but they're really, really faint. So there's no way that we can see them with the naked eye. But here you have the three types of brown dwarfs, so L, T, and Y, and you have approximate colors of the brown dwarf. And so if you ask me what's the color of a brown dwarf, then I will tell you that they're magenta. So the magenta dwarf, that's much nicer.
Maybe they get more funding if people referred to them as magenta dwarfs.
Yeah, just not brown. That's really, I mean, like even like that would be like orangey or purpley, like purple dwarf. That would be great too.
Were they trying to choose a name that sort of wasn't as like, because when you see things like white and yellow, you assume producing like more light, and I guess maybe they're just trying to choose a color that is not as bright or associated with like the production of light necessarily.
No, you're right. When the brown dwarf were theoretized, were thought of, so the theory was that you could have something that has a mass that is lower than a star, but still could exist, and then it wouldn't emit light. It happened in the 60s, and the ladies that talk about this for the first time in her PhD thesis, she just said black dwarf. This is how she called them. So the black dwarf. So a bit like, dark matter. Like dark matter doesn't emit stuff, so they're black. Thing is, black dwarf, it's actually the name of like also like a very special kind of white dwarf.
Oh.
That would be like a really, really, really old white dwarf. You would call it like a black dwarf. So that name was already taken. She just didn't know it because there was no like Google at the time.
Fair enough.
And then it became brown. But as you can see, like magenta dwarf would be actually better.
Yeah,
and
no kidding.
This is it. So we cannot exactly know what they look like. So that's another artistic tradition. This is JG 504b. So that's a maybe planet or maybe brown dwarf. Like it's about 12 Jupiter mass plus or minus 4. So you call it as you want. There you have its whole star. And this one would be about pink. So, and
pink dwarfs
again,
would be great
we don't
too.
know. Yeah, we don't know what it looks like. So we know it's bigger than Jupiter, so it has bands. But it's because Jupiter has bands, but we don't really know it. Because this is actually what, that is a real picture of a brown dwarf. So you can see it hit here in the H band. in the infrared, and here in the J band in the infrared. So that's about 1.1 micron. This is SIMP 0136. And what's really interesting is that, yes, you see it here in the infrared, but you don't see it here in the visible. This is I and this is R.
Whoa.
It's the same instrument, so it's not like a power. It's not because that's a small telescope and the other one is a big telescope. But you really need infrared to be able to see it, because you clearly see it like in the J and H band, but you really don't see it.
So I'm sorry to all of the visual, like the observers who are on our chat tonight. You cannot go out and look at this unless, as Katrina pointed out, you are a snake and you can see in the infrared.
Yes. Snakes can see in the infrared. That's true.
Has there time to become a snake?
And this picture was taken at the Observatoire du Mont Mégantic. Because in Quebec, we're lucky because we have this is our own observatory at University of Montréal. It's about a 3-hour drive from the city. And we get, I got a lot of time at that observatory doing my studies. And that picture was taken with this instrument. It's called CEPOP. So it's a play on word because it's an acronym, but it also means, like, CEPOP means it ain't too bad in French. So it's like funny because you observe with it and it's like, oh, how is it going? Well, CEPOP. And at 4 a.m. it's really funny, I tell you.
Well, I like scientists' sense of humor because there's a lot of like little, I remember, anyway, I'm not going to get into marine biology because that's my background, but even like the Trappist telescope being named after a Belgian beer is like, I find that hilarious. I think it's great.
Yeah, and there's a lot of, there are lots of instruments and surveys and astronomy that have like funny names.
Yeah.
My survey in my thesis was just called Weird because I was looking for those weird planets. So
that's great.
But I do hope Katrina, she says that she'd like to go at Mont Mégantic,
after everything's
time
settled. Yeah.
Yeah, I hope you get to go, and the best time to go it's normally in July, because there's a festival. So you have you have a talk in French at the beginning, but then you go up the mountain and you can actually put your eye. So instead of an instrument here, there's an eyepiece, and then you can look into a 1.6 meter telescope. Yeah, that's
so
really
cool.
nice. Yes.
Oh man. Okay, taking note of that for July 2021 because obviously it's not going to happen this year.
No, not this year, but yeah, road trip. That
road trip. That sounds good.
Yeah, yeah. Okay, so I'm not sure where I was. Oh, here, the first Brown Dwarf was discovered in 1995. It's called the GJ 228b, and then you see you have a big B because this is a brown dwarf, so it's not a planet. Like planet have the small b, and the brown dwarf have the big B, like the stars.
Oh, okay, cool.
But if you have something that you're not sure, you decide if you want to give it like a big B or small b.
So you can kind of choose.
Kinda. And then you write a paper, and the reviewer will tell you what they think about it. But this one is heavier, so it's more certain that it's not a planet. Here again, you can see it in the infrared. So you really need the infrared to be able to detect anything.
So we only have about 5 minutes left.
Yeah, I will finish with that last slide.
All right.
That will be my last one. Why do we study brown dwarf? 2 reasons. First, because when you look at the low mass brown dwarf, then they can look like planets. Planets can be really hard to study because if you study them, maybe you only know their mass or their radius. And so those are the typical, like, of the 4,000 exoplanets that we know, maybe you only know its mass or its radius. If you're lucky, you know both. But if you want to have information about its composition, then you really need a spectrum. And we've realized that those higher mass planets really look like those low mass brown dwarfs. So you can actually get a spectrum of those objects. The other reason why you would study brown dwarf is that they are actually the sun's closest neighbors. So that's something that you don't really realize. I mean, you know that it's the sun, and then the closest star from the sun, of course, is Proxima Centauri, that orbits a double system with the 2 stars of Alpha Centauri. And you see that they were discovered, in the 19th century, 20th century, 1977. And And then you have Barnard Star, which is an M dwarf. Again, Proxima Centauri also is an M dwarf. So I told you, right? Yeah, just choose one, and I will tell you it's an M dwarf. So this is Barnard Stars, discovered in 1916. And then the three next one, they're Brown Dwarf. But also note the discovery years, 2013, 2014. That's really recent for something that is so close to like only 6 light years to the sun. And we had no idea they were there until about 7 years ago. I remember the discovery of 0855. This is the coolest brown dwarf known to date. It's cooler than the freezing point of water. It's like minus 30 degrees Celsius. So that's really cold.
That is very cold.
And it's really close. But if it's really cold, even though if it's really close, it also means it's really faint. So this is why we needed a telescope in the infrared to be able to detect it, even though it was so close. Because Barnard Star, Proxima, they're all really bright, but not those brown dwarf. So that's the second reason to study brown dwarf, because they are the sun's closest neighbors.
That's very cool. And it's wild that we don't know. I mean, that we're only just figuring this stuff out now because we didn't look at it right before.
Yes, exactly. Like 10 years ago, they wouldn't be in this graph, and we had no idea. Yeah,
that's wild. Thank you so much for telling us all about this stuff. This is so cool, and it's stuff that I think, especially given the lack of funding, that folks just don't hear about that often.
It's just because it seems, I can talk to you about brown dwarf. Like, why?
But this is why, because it's so cool. It's awesome. And they need to start calling them Magenta Dwarfs. Someone needs to hire a PR person for brown dwarfs. Yeah. So we answered the naked eye brown dwarfs question. This is an interesting one. I'm just going to ask it quickly. John has already got his video up, which means I assume he's getting antsy and ready. He's so okay. So we have a quick.
He also has a hat, so I really like it. It's like a professional astronomer.
Yes, it does. It's all about the hats.
Yeah.
And oh, good, my cat broke something. So the question is, can brown dwarfs have habitable zones?
Well, no. A brown dwarf, so like a 50 Jupiter mass. It's like it doesn't emit enough light to have like a habitable zone. Maybe when it's really young, but it's not something that you could really look for life. If you have something that is a bit weirder, like if you have like a brown dwarf orbiting a star, then maybe you could have something with like a planet around the brown dwarf.
Right.
Maybe they would be like a system, but it's not. We don't look at brown dwarf to search for planet around them, because I'm not sure how you should call that object. If you have a brown dwarf and a planet around it, because if to be a planet you have to orbit a star, right?
Oh no, I guess it'd be a moon. I don't know.
A planetary mass object, and they are actually the first picture that we have, like the first directly imaged exoplanet. We usually don't refer to it because it was discovered in 2004, and it's an image of a planet around a brown dwarf, so it doesn't count. So like the actual first image of a planet around a star was in 2008. So that was a real star, but I'm not sure how you should call a planetary mass object around a brown dwarf.
We're gonna have to come up with a new name.
Because if you have like a 1 Jupiter mass, that same object, and you put it around a star, that's a planet. But if you put it around a brown dwarf, then maybe just a binary system, like a very low mass binary system. Boxes, I told you, it's about the boxes.
Yeah, it's about these boxes.
Planetoon.
One of my favorite.
That's really cute.
Yeah. Planetoon. Oh, that's adorable. One of my favorite metaphors, and I'm sure people who've joined for other streams have heard me say this already, but one of my favorite metaphors for this ridiculous naming thing is, would you technically call a hot dog a sandwich? Because it's something with bread on either side.
Yeah.
So is that how you define it? But then is an ice cream sandwich a sandwich because it has non-typical ingredients? What about an open face sandwich because it only has one side? It's just it's surrounded if you hot dog properly. Thank you, Heather. You're right. It's true. There's certain opinions about this particular subject.
No, and if you go like if you have a corn dog, then
That's true.
Is
Then
it like a hot dog? Is it a sandwich? Is
what
it
is
something
it? Is
else?
it both?
Yeah, what
is
is
it?
it?
Something else? Do
I
we
mean,
have to
if
come up
you
with
have
a
it
new
on a
name?
stick, then it doesn't count, I guess. But if you take the stick out, then
What is it? Yeah. Oh,
yeah.
we could go on for hours about this. Thank you again, Frédérique. I really appreciate you being here.
My pleasure.
And sharing all of this wonderful information with us. It's fantastic. And John, you have unmuted yourself, so I assume that means you're ready and set up to show us the night sky.
Yeah, well, that was a great talk, Frédérique, and you know, I learned a lot. I was listening while I was sort of setting up all these cameras and stuff, and it was great. Thanks so much.
Thank you.
Yeah, all right. I think I'm ready to share the screen and talk about this, and because I want to talk about my setup.
Perfect. Okay.
All right, so let me know when you are ready.
You are good to go. We are patiently awaiting your shared screen.
All right. So here's what we got. I've got the DSLR hooked up to the German equatorial mount on the refractor telescope. So this is showing a star here, and Starlink is supposed to pass right by this star. So we'll call this camera A, I guess. And over here on camera B, I've just got it centered at, that's Arcturus here. And so this camera is my son's like $120 reflector telescope. And so this one has a red dot finder, and hypothetically, as we see Starlink somewhere in the sky, I'm just gonna go point it like I'm pointing a cannon at a target kind of thing.
Okay, cool.
And so hopefully the prediction is correct, and I can bring up the prediction here. Definitely losing my night vision. So we got about 5 minutes until the first ones come. So this is just one of the satellites in the group, and the other ones in the, so they usually launch in groups of 60. And so they'll either all be in a line and pass through this spot, or they'll sort of be side by side.
Okay.
So I hope you can see my mouse. So this star that I'm pointed at now is the star that's centered in backyard EOS right here. So that's this star right here. So if everything is lined up, the satellites will pass through this frame.
Cool.
In theory.
Awesome. Okay. And I'm gonna, if you're at a good pause point, I'm gonna give a little bit of context for what Starlink is for folks who don't know, which I mean, almost
Absolutely.
everyone knows now. But what's that?
We have about 5 minutes before the attempt.
Okay, so I will just quickly go over what Starlink is. Excuse me. Starlink is a network of satellites being launched by Elon Musk in order to provide, I believe he's providing internet to the, well, the goal is to provide internet to everybody. However, to do that, you need to launch lots of satellites. So the way that he's launching them, and this is the same way that satellites in general get launched, is they all go up on one rocket. The rocket gets up into space, and then they go boink, 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 and shoot off in very close to the same direction, but all bunched together. And so that's why you end up seeing these massive groups of streaks going across the sky. Slight digression, one of my friends works at the University of Toronto's Institute for Aerospace Studies, where they also launch satellites, just not Starlink. They're usually, they're any number of things. But for the first couple months, all the satellites are bunched together, and it's really difficult to figure out which one is yours. And so they spend a bunch of time trying to talk to them, and then going, oh, wait, no, that's France's. Okay, we'll send that. Okay, France, that's yours. Sorry. And then here's this other one. And they spend lots of time figuring that stuff out. So when we see these, you'll see lots of pictures of these like streaks going across the screen. And those are all those satellites passing through our view, all in a big group. They do get dimmer as they get further up, and you only typically see them right after sunset or right before sunrise, because they are still lit up while we here on Earth are not. They do cause some problems for astrophotographers and for observers as well, because you see them coming across your field of view. One of the bigger areas that they do affect, they actually do have an effect on science as well, because they broadcast in radio frequencies, which is, so it makes radio astronomy a little bit, well, a lot more difficult. So that is a rundown quickly on the facts of what's going on with Starlink. Lots of folks have very strong opinions about it. The RASC has not taken an official stance. We want to educate and share. And so that's what we're doing tonight. We're taking a look and seeing if we can see that. So we've got what, T-minus 2 minutes or something like that, John?
Yeah, and I'm actually gonna add, if I tilt this, we might, like, they can be pretty bright. So hypothetically, if I just point my laptop screen at the sky, you might
Okay.
also be able to see them snaking across there.
So I'm gonna spotlight your video.
Okay, so we
Um,
also got, so we've got 3 places to watch here. We've got, and I'll let you know when they're going to appear on this screen, which is where they're most likely to appear. The field of view on this, the Newtonian is really small. And the reason it has to be small is because if I make it really big, I can only do like 5 frames per second, and then it'll be all over the place.
right.
So
And that one, it looks like it doesn't track, eh? So it's not
it
following
doesn't
the
track.
movement.
So this one,
Okay.
I mean, they're moving, they're booking it. Like they'll cover the whole horizon in about 4 minutes, horizon to horizon. And so I keep checking over my shoulder to see if they're coming. I believe they're going to start coming right here over the neighbor's house, and then they'll pass straight overhead. So the refractor here is almost pointed straight up at this star, which is right next to Arcturus. And I'm really hoping you'll see them in this camera feed, because that'll be really neat.
You are nothing if not prepared, John, with 3 different setups here.
You can always have a backup and a backup for your backup, but sometimes
You never know when you might need it.
well, I mean, that's what stargazing is all about. Like you attempt things, and sometimes you're not successful. Maybe you're looking for some galaxy that to check out for your observing list, and it takes you many nights. Or I lived in San Francisco, and all I wanted to see was M101, and it was maybe 2 years before I actually got to Glacier Point in Yosemite National Park that I was actually able to get it into a telescope.
Wow.
We couldn't see as bright. I mean, it's not a super bright galaxy. You sort of want to be out of the city, but even in the burbs, I never saw it, and I checked almost every night.
Oh man.
And it wasn't until I borrowed a larger telescope and was out into a place that has the darkest, almost as dark as we get here in Nova Scotia and Kejimkujik, that I was able to see it. All right, let's do a time check.
Yeah, it's 9:02.
9:02.
Fingers crossed.
Okay.
10:02 there.
So
Any sign of anything yet?
That's the time when the first one should be coming over the horizon.
Okay, so we have like a 4-minute sort of window, maybe 2 minutes till it's directly overhead.
Yeah, and again, these aren't super bright. So I've been staring at this laptop screen. So it's also possible that at the magnitude that this particular constellation is at, that it'll be difficult for me to pick up from the city. I don't know. It's always an experiment with this kind of thing.
We'll try. And this is actually a good metaphor. And John, feel free to keep looking while I vamp. It's always a good metaphor. Sorry, not a metaphor. It happens a lot in astronomy where, especially things like with the comet that's recently been coming by, Comet Atlas, where everyone was really excited for it to get really bright right about now, and instead it broke apart. So it's things change, and they're not always exactly the way you expect it to be. There's a project I recently found out about that's happening out west called Recon, where they have a series of telescopes that runs down from just north of the border in Canada down through to Southern California, where if they find out that an object in the Kuiper belt might pass in front of a star, they all take photos at the same time. And that way, if there is an occultation of that star by some Kuiper belt object, you can figure out from all of those telescopes what the size was, so that we can learn more about those objects that are further out in our solar system. So there's some really neat stuff you can do, but again, you never know, and there's only sometimes a 30% chance that it's gonna pass even in front of that star from any of the telescope's perspectives. Hard to know.
Yeah. So we might not see it with the naked eye, but I think we might see it in this in the view on the left here. So which will be neat.
Backyard EOS.
Yeah, and there's also there'll be a couple passes over the next 10 minutes. So if we miss these first couple satellites, there might be.
Let's try again.
Later, as well. And I mean, the cool thing about just stargazing in general is if you attempt to find one thing, you'll often find another. So I was out stargazing a couple nights ago, looking for Starlink, and I saw a satellite that just was tumbling. So that's where you might think it's an airplane flashing its lights, but it's moving much quicker, and the flashes are slower. And that might be a satellite that's just slowly turning end over end in space, and its solar panels are reflecting light at you. And so that's always a neat thing to catch as well. And sometimes you'll see them that they'll be flashing brightness at you for 10 seconds and then they'll turn off and then they'll come on again. And that's,
Oh, that's cool.
something,
For a while, although I think it's over now, there was something called Iridium Flares where some of the old satellites had, they would flash brighter when the sun caught them. And so they'd end up in these really fabulous, like big flashes of light. But I think that generation of satellites is all done now, eh?
Yeah, there might be a couple of them still up there, or they're in parking orbits. I haven't seen one of those in a few years at least, but they used to be really fun to photograph.
Yeah, no kidding.
As well.
Frédérique, if you want to turn your microphone on, you're welcome to join in our conversation. Don't feel that you can't chat while we're all hanging out.
You seem to have a good conversation going.
We want to talk with everyone.
I was thinking that this week I was talking with non-astronomers, but also like amateur astronomers, like people that just don't really look at the sky. And I was telling them what it looks like an actual observing night. And I was telling them about sky flat. So this is when you observe a sunset through a telescope. So you just look at, you have just like a camera, and then you look at the screen, and what you see is like saturated, and then it gets fainter and fainter and fainter, and then until it gets dark. Mm-hmm. That is really a non-romantical way of like looking at a sunset. And the people that I was talking about, they were like, so they don't have this idea of like astronomy. It seems like so romantical. You look at stars and the universe with a telescope, and I was telling them, no, it's like just really boring. You just look at a screen for like 45 minutes and it just gets dark.
Oh,
and then that's your data.
And that's actually, so you mentioned this earlier in your talk. For professional astronomers, the overlap between professional astronomers and observers there's not very much of it. Often professional astronomers are like more focused on that sort of data collection and like programming the telescope to do what you want it to do.
Yes.
Whereas the folks who join the RASC, for example, while there may be some folks who enjoy that sort of thing, a lot of them do that go out and look at the stars and say, oh yeah, there's Ursa Major, and here's how you find Draco, and this, that, and the other thing. Where if you ask a professional astronomer that, they kind of go, huh?
Yeah, it's like really recent in my life that I can go like, and then you arc to Arcturus, and then you spike towards Spica, and then
yes, yeah.
that's fairly, it works better in French, I have to say, because you archer vers Arcturus, piquer vers Spica, but
oh, that's good. Yeah, that's fair.
But it's really recent that I can do that. So if you ask like most astronomy student, like grad student, to tell any stars, I'm not even sure that I can like pick out the Big Dipper.
That's fair. I understand. If they're not trained to be looking up at the stars specifically, so it's
no, it's really just another way of looking at it. It's really like through the computer, through it's just another way.
Mm-hmm.
Even the name of the stars, sometimes there are some like messy object that I just know they're NGC because I just don't know which one is which messy.
Yeah, it's like they're blue and they're up there. Yeah.
I almost thought, going into an astrophysics degree, I'll be such a good, astronomer when I graduate. And it's really not true. Like, you get really good at calculus and computer programming.
Yes.
The stuff that translates into science communication and whatnot. It's you really have to get back to the books and look at things from a different angle.
Yeah, it's really physics. We often say astronomers, but it's really astrophysics. So like the background is actual physics. And
that can be really difficult to explain. Like, my dad asked me what I do, and I'm like, I'm not even sure if I know. Statistical mechanics or something like that. Like, how do you explain that to the general public?
No, that's really hard. There's like all the condensed matter physics. That's like you have a ceramic, you just like cool it down, and then it becomes like a magnet. That makes no sense. It just doesn't.
Well, this is all far above my head because I'm a marine biologist. Oh man. I wanted to briefly mention, because Dan's in the comments, Dan Meek, who's on he's getting the robotic telescope set up with us at the RASC. He's using the robotic telescope to image the Pan-STARRS comet tonight, hopefully. And he's using the DSLR that's piggybacked on top of the telescope. So that's going to be something interesting. Maybe Dan, if you've got, so that's, actually he just sent the link to to what the rest of the night will be. Woohoo. So Dan, if you manage to get a photo of Pan-STARRS, I will upload that and share it with in the YouTube description afterwards. Now, John, an update on what's going on with Starlink.
So, I mean, this is almost a good experiment because they were predicted to fly over. They were predicted to be between magnitude about 3.5 and 6. So 6 is about the limit of what you can see with the naked eye in a dark sky. So it's kind of interesting that this round, I think this was satellite group 2, which means that I believe that means it's the second launch to go up. And that probably means that, yeah, they're in their higher orbits, and from a city, we're not seeing them.
Maybe, yeah.
So
that's okay. Thank you for trying.
That's interesting data right now. So I guess in a minute or so we can, if you want to try one or two targets, I know we can get M3 here in the telescope, and then maybe just look at Mizar and Alcor and call it a night.
That sounds good. Yeah, let's take a look. Whatever you've got to show us. This is the joy of city observing, and I will mention as well that the moon tonight, if Katrina is leaving us, and I totally understand why, because the moon is almost new. It'll be new on, I think, Friday. And so it's nice and dark out there. But it means that we don't have an easy object to look at in the city. The moon is one of the best objects to look at if you're in a city with light pollution. Excuse me. And so John's going to show us. John, you said Mizar and Alcor, and what was the other one?
Yeah, well, we're right beside M3, I believe, right now.
Oh, sweet.
So
okay.
This is the globular cluster. I think it's really neat because it's got 3 stars that sort of surround it like jewels. So it's kind of unique in that way. So let me just, using the hand controller here on this is a go-to telescope. So
while you're using your telescope, Peter from Toronto asked if you have the Mighty Mac, C90 Mighty Mac out tonight.
I do not. It's upstairs. I've been using it on this workbook for 50 things to see with a telescope that I talked to Jenna about, and it will be coming out soon.
This is a different one, but John writes great books is the point.
All right. So Messier 003. You'll hear the scope slewing. I think that the slewing sound of a telescope is one of the most beautiful sounds in the world. I love it. Especially the bigger scope. The dome creaks, it beeps, I guess, so that you don't stick your fingers in the wheels as it's turning around. And you have all these computer sounds and whatnot. And I'd say, Mary's, you can hear the elevators going up and down too. So there's all sorts of wonderful sounds in the observatory.
Soundscape. You should change your cell phone ringtone to the sound of motors whirring.
It's a beautiful thing, really. Okay, so I'm not sure if it's in the shot here. So you can just sort of follow along. This is some imaging software for DSLR cameras. And basically what you do is you just type in the target name, and this helps with the file name. You put in the duration of the exposure that you want to take. Okay, so here we're in the city, so usually 15 seconds, and we're overblown with light pollution. An ISO of 3200 is good for DSLR cameras, at least this one. And so basically you just start capture, assuming the telescope's in focus. It'll count down from 15 and then download the photo onto the computer. And this is a very, very sort of entry-level way to do astrophotography, telescope and a DSLR on a German equatorial mount.
I'd like to point out that there are easier ways to do astrophotography too.
There are. So for deep sky objects, this is
a good one. And anyone who's interested in deep sky astrophotography, actually, we were running a second session on astrophotography. We ran one yesterday with Paul Owen, who's a volunteer of ours from New Brunswick, and we're running another one on Tuesday next week if you want to join in for some more in-depth deep sky astrophotography.
Yeah. Okay, so it looks like my alignment wasn't so great because it wasn't fully dark when I set up the telescope, so that was kind of tough. I can see that we're actually missing the cluster altogether, and that's sort of too bad.
Do you want to realign, and I can talk about, I don't know, globular clusters or something like that?
I wouldn't want to risk it just because I'm not sure if on the deck here I have the alignment stars, so we might be going over time. But let's do the double star, and we'll see how we do. So another failed attempt, but at least we're having fun.
We're trying, all right, and that's what astronomy is about.
Yeah.
And we were lucky because there's no clouds, because astronomy is mostly looking at clouds.
It's true, yes. And Simon pointed out that he did buy telescope parts, or possibly an entire telescope, like last week. So he's the reason that he's been having bad weather in Calgary. So sorry, Simon.
Oh, just a second. I gotta let my dog in the house here.
A dog, a cat, oh la la.
He just got a T-Rain. Fine, Simon. Our host who's been on the previous sessions, he has 2 cats and they're named Aries and Venus.
Yeah,
Oh,
so
cute. I have budgies.
Hi.
Oh, hi. That's a real star.
You have, oh, hey. You said you have canaries and budgies?
I have budgies, yes, and one of them is named Io.
Oh, amazing.
Oh, that is a great name.
We're gonna have to have like a sharing session. Anybody who has pets named after any type of astronomical phenomena or object, please voice your pet names in the chat if you're
Or people, could be people too.
Could be people names. Actually, we do have a member who's, oh wait, no, I shouldn't share personal information, but we have a member whose daughter is named after a star. Oh, there's a Stella. Okay. That's always good. Oh. And we've got, yeah. Simon, do you know what Sophia's hamsters are called? I have never heard of space named hamsters before, I have to admit. Gluini. I don't know Gluini. Okay, I'm going to Google that.
I also had the budgie previously that was named Quark.
Oh.
And we hope it would get big, so we could call it Top Quark, but it stayed small.
That's amazing. That's great. I get it, Gluini. Like
yeah, lots of them, like Luna and then Cassiope.
Yeah. Cassie's a good one too. Oh, that's great.
This is so fun.
Yeah, I know. It's nice hearing what everyone's animals are named after. I love it. Cassie is a really nice one. I also do like the Neutrini. Oh, Neutrini would be adorable. All of these like subatomic particles turn out to be great pet names. Yeah.
Yes.
There's a song about quarks by Hank Green. Did you ever hear that one?
No, I don't think so.
Okay, I'm not going to sing it. I used to sing it at the Science Center for Children, who would stare at me blankly, but it's like totally accurate. A quark is a fundamental constituent of matter observed in 1968 from deep elastic scatter. It goes on very accurately, but it's yeah, kids would kind of just sit there and their eyes would glaze over. All right, John, what you got for us there?
All right, so this is Mizar and Alcor here.
Oh, look at those.
And actually, so these are fake double stars, and it's probably because I'm on a deck. So you can see how if each star is double, that means I stepped on the deck board during the shot. So let's try that again. But essentially, you've got, I believe, we've got Mizar and Alcor, and this one would actually be the double. And if the focus is great, you'll see that these stars are visual, the 2 bright ones, this one and this one. So without a telescope, you can see that that's sort of a double, and then this one is double again.
Oh, a double, as it were.
Or more like a double single.
I guess a double single.
Is the one
single double.
Epsilon Lyra.
For those who do not know about Mizar and Alcor, they are the 2nd star in the Big Dipper's handle. So you can see these from a city, as demonstrated by John right here. And if you have really good eyesight, you should be able to see those two, the 2 dots that are further up in that image.
Yeah, so it looks like my focus could be better. So here's how you focus a telescope. What you do, this is called a full width half maximum. So you put a star in this little bullseye here, and what you do is you try to minimize this number, and just by turning your focus knob. And when that number is as low as you can get it, then your telescope is.
Oh.
It's one way to get it as good a focus as you're going to get.
So John was the first person who taught me how to focus anything in space in astrophotography. Prior to that, I was just terrible at it, and I hadn't really tried too hard. I just kind of gone, let's give it a shot. And the trick that John gave me was to find a brighter point of light, like a street lamp that's in the distance, and make that as fine a point as you can. And before that, my space photography was a mess, John.
Oh, yeah.
Awesome. You can see it's a little oblong, so I guess that would be the 2 bits, eh?
Yeah, so we can keep reducing the exposure and see if it splits the double that way. Let's try just 1 second. And we're probably going to be in for some nasty weather because, as Jenna knows, I just sold my red car that we used in our astronomy video series there last year. We finally killed it.
So sad.
But I used all the money and spent it on astronomy gear. So we've got a CMOS camera, guider, a designated astrophotography computer, and then all the attachments to go onto the different mounts so that I can use it on all 3 of my astrophotography rated scope. So we're probably in for a month of hurricanes and tornadoes.
John, how dare you?
I know. Sorry.
I feel like the astronomy community needs to get together and decide that we're going to spend all of our money in like January, sometime when none of us want to go outside anyway.
Yeah.
There you go. You can get to see that oblong shape, especially compared to the other stars.
January is the best time to go out because you have the longest nights.
You have a point, but it's -40.
Yes, and then you take a picture of like the temperature on your dashboard of your car, and then you show that you're a real.
That's a very good point. That's a very good point. You get bragging rights.
Yes.
And as Heather says, less atmospheric disturbance.
Yes, and it's better for Fred too because you have less background.
There you go.
Thermal background.
There you go.
Hey, there it is. There's that double star.
Oh, cute.
So this is more similar to what it will look like through a telescope. With your eye, you'll be able to see that with your eye through the telescope, you'll see this double split in almost any telescope. So
that's cool. Heather pointed out that it looks like a potato, which it does.
Yeah.
But honestly, so one of the things that I think is kind of cool about astronomy is that you see these beautiful pictures of the Hubble telescope is taken of these amazing colorful nebulae and things like that, and they don't look anything like that if you look through a telescope.
No.
But yet it's still really exciting when you see it. Like going out.
I mean, when I look at Jupiter and I see the moons, every time I get goosebumps. Just so cool. I mean, it's like I'm like Galilei. It's like, look at there. They're just there.
Exactly. Yeah. And it feels so cool to see it yourself, and it makes you appreciate everything that's going on around you so much more when and it's one thing to see a picture, but when you can look through something and just see through mirrors and lenses planets that are so far away, it really brings it all back. It's so cool. And as Simon said, seeing Saturn for the first time, that's like what does it. That's why people buy RASC memberships.
Yeah, that's what got me into astronomy, seeing Saturn through a telescope I bought for $13 at the pharmacy.
Wow.
And it was like HD. It was perfect. It must have just been perfect seeing and everything. And then
that's awesome. John is the king of like budget telescope stuff. He's good at this stuff.
Well, it's gotta get past, it needs the wife approval for me. So
we had the same conversation in a one of our previous in our last video about beginner telescopes with Chris Vaughn, where he was like, also you have to run all of your telescope purchases by your significant other. And I pointed out that you can always get into the hobby first and find the significant other afterwards. And he's like, yes, go shopping for both a significant other and a telescope.
It's hard to say which one would be more expensive. Okay, so I'm doing M51 a shot just to see what happens here. Because you never know.
Woo!
Yeah, there's something there.
There's some blur stuff. Oh yeah. Okay, so M51 is the Whirlpool Galaxy.
Whirlpool Galaxy, yeah. So you can see all this noise is the light pollution from Halifax, because this is actually over downtown.
Oh wow.
But this is sort of it's 2 galaxies. You've got a larger one here and a smaller one here, and they're connected with by gravity and through this gaseous arm that passes between the two. So hypothetically, if we were to take photos like this all night, get a couple hours of data, you can separate the signal from the noise and actually make one of these pretty pictures. That would make the magazine.
Can you zoom in a little bit on M51 there, John?
Yeah, we can try. I'm not on my monitor is not very good, but you can see a little bit of spiral structure there.
Yeah. That's pretty good. And this is again emphasis on how excited astronomers get about fuzzies. But I mean, that's pretty cool to be seeing that from Halifax, that you can find that.
Yeah, and if you use the Burke-Gaffney Observatory to do it, it can do a really wonderful job, and it'll take hours of photos and stack them all together for you. That's the Twitter controlled telescope here in Halifax.
Your telescope is very cool that you can control it by Twitter. So that's the Burke, as in Burke, Burke-Gaffney Observatory. If you're looking for that online.
Yeah, so you can you tweet to it, you say #authorize I love astronomy, or I am this person, I love astronomy, and you'll get authorized, and then you can take, I think, 3 pictures a night with your sort of beginner account.
That's pretty cool.
Yeah.
There's a question from Simon. Just, can you process out the light pollution easily, or is it trickier?
So what you do is you take you take several pictures so that you have about an hour of data in total, and then you can subtract it out in processing. So you stack them together in stacking software. If you're just using a digital camera like this, it's called Deep Sky Stacker. So this is the software. So this will put them all together, and you stack the raw files, and so that saves. It basically is a photon counter, so it counts up all the photons, and it'll help you subtract the noise and from your images.
Cool. There's also some filters that you can buy that'll filter out some of the light pollution too.
Yeah, I forgot to put it on, so I have a light pollution filter, and that would have helped a little bit.
Don't worry about it.
Yep.
That's awesome.
But a lot of it's just experimentation, really.
Yeah, and this is the kind of fun thing about astronomy, is that first of all, you can experiment, and usually things will not go wrong. And second of all, it's a pretty solo hobby. Like, you can get together with people and do it if you want to, but if you fail, you can do it quietly and by yourself if you'd like.
Perfect for this summer.
It's perfect for this summer. It's true. Yeah. Especially when we can't be with everybody, it's a great hobby to pick up on your own. That's not bad. You can see the 2 cores. I'm gonna, for the folks who don't know what M51 looks like.
Let me just stop sharing, and you can.
I'm gonna just quickly share a photo of, like, taken by a big, fancy, expensive space-bound telescope. That's from Google Images, so bear with me. So that's what the galaxy looks like. It's two galaxies. Two galaxies that are interacting with each other. And so you can see. I'm gonna shift this over so I can see my face isn't blocking it. There's the main one with 2 spiral arms, and then there's that little one off to the side that's caught one of the arms. Ooh, there we go. So that's if you could open your eyes for like hours and hours and hours and hours. We are just opening our electronic eyes, our telescopes, for several seconds, so it doesn't end up looking quite as fabulous. But still very cool that you can see it.
You also need multiple filters if you want to have all of those colors.
That's true. The filters do help. Yeah.
Yeah.
All right, I will stop share. John, do you have anything else you want to show us tonight, or are you feeling pretty good?
I'm feeling pretty good. I was gonna, really quick, if I had one here, show what a Burke-Gaffney Observatory picture of that would look like.
Oh, sure. Yeah, absolutely. And while you do that, there was just a message from Peter, who stepped outside, and apparently Venus is stunning in the northwest sky in Toronto right now. And so once we wrap up here, I recommend that you go out, and I know you're not all in Toronto, but whoever is, go out and take a look. And then for those of you who, I know there are many of you from Calgary, wait 2 hours and then go take a look yourselves. Okay, that's pretty cool from the Burke-Gaffney Observatory. So that's even same light pollution as you have where you are.
Yeah, same light pollution. This is 300 seconds worth of data. And this is an unprocessed image. So in the morning, the computer would take, a flat field and subtract the bias, get rid of some of this noise. And then he's taken this one in a blue filter, and you can take red, green, and blue and create your color image with a command, with a tweet. It'll combine them all together.
So cool. So cool. Yeah. Also, I'm sorry for basically rubbing Venus in your face, Calgary, because I said, yeah, Calgary can go out 2 hours later, except I forgot you guys have terrible cloud. My apologies. Oh boy. Awesome. John, thank you so much for showing us around the night sky tonight. That was great. It was so wonderful to see what's going on out there and see some targets that you can see in the city. Like, it's nice to be able to see things that are accessible for everybody,
Yeah. There's, I've got a very limited, so my house is right here and there's a big tree right there. But the objects tend to pass through my field of view. So as the interesting things come by, I see them when they're there. But from the city, there's all sorts of open clusters like M35. You can see globular clusters. I have a 12-inch Dobsonian telescope that I use for doing visual observing here in the city. And you can check off pretty much all the Messier objects from here, which is neat.
That is awesome. I'm going to mention very vaguely, in very vague terms, there may be some observing stuff that's coming up shortly. And I mentioned this briefly before, and John may be helping out with that. John, can you self-promote some? Because people are calling on you to self-promote.
Sure, yeah. So my first book, which is still pretty popular, is 50 Things to See with a Small Telescope. And, so most places you can pick that up for about $10. I'm not sure how much it is in Canada. Might be closer to 15 here. Then I became professionally published with 50 Things to See with a Telescope, 50 Things to See on the Moon, 50. My wife and I collaborated on 50 animals that have been to space. This fall, we've got 50 space missions that changed the world. Yeah, everyone's favorite seems to be the Moon book. Jenna?
I love it. It's great. It goes through, sorry, I'm going to promote for you, but that's okay. I hope that's all right. It goes through the different views that you would get with binoculars, refractors, and reflectors. So no matter what you have, it shows you what you'll see, and it goes through everything by the day of the moon that it's on. So when you can see it and cool facts that go with it. I think it's fantastic. It gives great visuals, and it gives you a good idea of what you'll actually see out there.
My favorite thing about that book was that the moon tells us the history of science. So starting at the North Pole, going all the way to the south, the craters were named after prominent scientists and philosophers throughout history. So it was neat to, as you explore each crater, to go and Google who it was named after and what they accomplished in life. And I thought that was really neat. And there's 28 or so craters named, actually 28 or so craters named after women. I think 14 are on the near side, and then we've got several craters named after Canadians that you can find as well, and that's a whole lot of fun. They're not in the book yet. Maybe they'll be in the sequel. They're a bit more challenging, but definitely there's lots to see on the moon.
Awesome. Thank you for promoting yourself. Thank you for contributing your books to the world. Thank you for contributing your views of the night sky to the world. Frédérique, thank you for contributing all of your knowledge to everything. It's been great to have you both on. I'm so glad we got to hang out tonight. Thanks everybody else for joining us as well. Do you guys have any last minute thoughts that you wanted to share? Frédérique, do you have anything you'd like to promote?
No, I think that's fine. I don't have any books. But interesting about the craters, it's only less than 2% of the craters on the moon that are named after women. So let's hope that this will change.
Let's hope that this will
with
change.
the new things that we will discover. And it's a good start with the W1 that is now named the Roman Space Telescope.
Exactly. Things are going in the right direction, which is great. And I'm so glad that you shared the W1 telescope with us. That's great. Thanks everyone. We really appreciate you being here. Our next star party won't be for another month. We're taking a bit of a break, but please do join us again and keep an eye on our website for what's going on in the future. Tomorrow night, we have a talk by Randall Rosenfeld, who's our archivist, and he's talking about Truth at the Eyepiece and how our perceptions of what we see through telescopes have changed over time. So that's tomorrow night at 7 o'clock Eastern time. Thanks everyone for joining. Thanks again, Frédérique. Thanks again, John. We'll see you guys all soon.
Of course. Bye, John.
Have a wonderful night, everybody. Bye-bye.
Take care.